Good afternoon, JEE enthusiasts. Welcome minions to session number 4, the last session of mechanical properties. Last lecture we have talked about surface tension. Today we are going to talk about elasticity in solids and how the volume changes in the fluids. So today is all about deformation, stresses, strains and elasticity. With me, Shreyas, your host, your anchor for JEE Enthuse channel. Welcome. What a lovely afternoon it is, and we started our day today at 7:30 with a very grand Menti quiz, and what a lovely participation. It was so cool, so amazing to see so many of you out there waking up at 7:30, and glad you all could join. And I saw that many of you felt that that time was very comfortable because it was before your school starts. So I'm glad that you guys have enjoyed that session, Menti quiz. And in case you have not watched it or you could not participate in it, go ahead, watch the replay. There were some really killer questions in that. Hello Shreya, Kirito, Asmi, Ankit, Fida, Ranjit, welcome aboard, welcome. Arthi Pandu was also there. Hello Anisha, welcome aboard. I hope everybody is doing good. Hello, good afternoon, Uncharted. So let's begin with the session. So all those who are new students out here, so this is Shreyas and I teach physics and I also anchor this channel. So guys, I have been training students for a very long time, and many of my students now are in very good institutes like IITs, NITs, BITS, you name it. And many of my students have produced, they have got ranks less than All India rank 100. Many of them have also cleared KVPY exams. They have secured top positions in KVPY. So that's why I'm here, so that you can get training from the best teachers in the country, and you can also be over here on this count out here. So I really hope you're going to make me and all the teachers who are teaching you very proud, as well as your parents. Hello Jumna, hello, welcome everyone. So let's begin today's session, and before I forget, do not forget to hit the subscribe button in case you are new to this channel, because only when you subscribe you will be getting all the regular updates of this channel. And today, in fact, at 4 o'clock there is going to be a special session for the board examination. The board examination announcements are going to be made by the HRD minister, the education minister, and we are going to see it live over here. So do not miss that. So hit that subscribe button. You will get all the notifications then. All right. And we are probably going to get a better clarity on how the board examinations are going to be conducted. So it's going to be at 4 o'clock. You can get your parents, your friends, your relatives, everyone along. Spread the news, guys. Share it across. And do not forget to hit the thumbs up button. Yes, go ahead, smash that like button, guys. Unless you smash that like button, YouTube is not going to recommend you our videos, and also we are not going to get that energy. So go ahead, smash that like button. It's free. All right. So let's begin. And this is the schedule for tomorrow. So today, like I said, 4 o'clock there is going to be a special session. Friday there is going to be a recorded premiere session of capacitors, the last session of capacitors. So on dielectrics, charging and discharging. So that is what it is going to be. On Sunday you're going to have a chemistry Menti at 9 o'clock, and like I said, today morning there was a physics Menti, so you can watch the replay later on in case you have missed it. All right, so let's get going with solids and elasticity. Let's get going, guys. Come on, keep the chat box active and let your Josh not die out. Let it be high. So do you think any object can be truly rigid in nature? So truly rigid means that you cannot deform it. Even if you apply a force, it does not get deformed. Well, you might think stones, diamonds, etc. are almost rigid. Well, they're almost rigid but not actually rigid. In fact, no body in this world is actually rigid. It's near to a rigid body. It's an ideal concept. So objects like a wooden box or steel rods or even plates, let it be of ceramic, plastic, doesn't matter, or rocks. All these bodies, although look rigid, they are capable of undergoing certain deformations and we study their deformations because it will help us understand many things. Like the deformation of rocks helps us understand earthquakes, tsunamis, etc. The deformation in steel rods, etc. helps us construct very strong earthquake-proof buildings which can also withstand very heavy weights. Also, you can, with the understanding of how the behavior of steel, aluminium, iron, etc. is, you can construct bridges, you can make cars, vehicles, and ships and aeroplanes. Also, by understanding how ceramic behaves or how plastic behaves, one can make very nice, durable and long-lasting plates or any other household item, because you do not want to use up too much of material to make it stronger. So the design process involves making use of very little material as less as possible to save money, of course, and to save the material costs, etc., and to give you a sturdy and more efficient design. And so all the things around you, the way they are designed, is based on the strength. Many of the processes involve a very big team which will design whether it can withstand this load, whether it will break, at what point will it break. So all these things are required. So we are laying the foundations of these things in today's session or in this chapter. Now, what is the meaning of elasticity? So elasticity means, hello Sudan, welcome back. Hello Richu, welcome. So what is the meaning of elasticity? Elasticity means a property of a body. Listen to me guys, and I hope you are making notes. It's a property of a body to regain its shape and size when deformed. Example, kutte ka dum, matlab guys, the tail of a dog. You try to twist it, what happens? It comes back to its original shape and size, isn't it? You might have heard that proverb. Yes, correct. So that is a very good example of elastic behavior. And what is then opposite of elasticity? The answer is plastic behavior. Okay, so we are going to come to that. So why does this happen? We'll talk about it. Understand, any structure is made up of molecules and atoms, and these molecules are joined to each other with something called as bonds. So you can think of molecules as masses, and you can think the bonds like springs. If the molecules are decently spaced, the distance between them is the bond length, that's their equilibrium distance. But if two molecules are full high of Josh and they come close to each other, then they are pushed back by the spring-like forces, which are because of the electromagnetic forces, and if they go far away, then they are again brought back. So they are maintaining some equilibrium distance. Now if you think of any solid, it could be this plastic, it could be this pen, it could be this board, it could be you yourself, it could be the table on which you are keeping your laptop, or the chair on which you are sitting. All structures around you are made like this. They are made of molecules and spring-like forces. So the moment you apply a force, there is a deformation, and you will see that deformation is produced because all the springs are going to get compressed, elongated, deformed, etc., and there will be a change in shape and size. And when you release that force, again it will come back to its original shape and size. I hope this is clear. So on applying a deforming force, the molecules will change their relative positions, and that's why you'll see a change in the shape or the structure. Now, like I was saying, there is a difference between elastic behavior and plastic behavior. So when you pull a rod or deform a body, you will see, you can pull it and leave it, it will come back. So that is elastic behavior. And I just told you that elastic behavior, best example, the tail of the dog, and there can be more examples. Like you can take a scale, guys. All right, you can take a scale. I don't know where my scale went. Let me just try to figure it out. Oh yes, my scale is here. Okay, so the scale, if I bend it and leave it, it comes back. If I bend it and leave it, it comes back. So this is elastic behavior. But if I bend it too much, you know what's going to happen? It's not going to come back. So that is plastic behavior. And many of you would have seen that kind of behavior when you would have eaten with spoons which are very thin. sometimes you go to a marriage hall, guys, I'm telling you, I had gone to few marriages. The spoons that they used in that marriage hall were so pathetic. Yeah, matlab, the moment I put my spoon in my plate, the spoon bent. That was plastic behavior. Spoons are not meant to be plastic in the first place. All right. Rubber is elastic behavior. All right. A lot of people are now remembering how many spoons they have bent and how many scoldings they have got from their parents now. Okay. So plastic behavior is also shown by clay. You can deform it. It regains some new shape and size. You can easily deform it. So that's plastic behavior. Or the cheese on the pizza, guys. Okay. Today we are talking about pizza now. We have talked about rolls, we have talked about momos, sandwiches, and so many other things. So the cheese on the pizza, you extend it, leave it. It does not come back. If it comes back, trust me, it's a very bad cheese on that pizza. Okay, so you elongate it, leave it, it stays there. That is plastic behavior. Yes, another tasty session. Hello Janvi, hello Shreyas, welcome. Okay, all foods out here. So let's talk about the next thing, which is stress, but not the exam stress, guys. Let's talk. Oh, sorry. I think this slide was not supposed to be here. But anyways, so let's talk about stress, guys. What is stress? Now, stress is nothing but how much force acts per unit area. The concentration of force. It's very similar to pressure. Yes. So it's very similar to pressure, but pressure is generally used with liquids or gases, but in solids the word that you will be using is called as stress. So it's force per unit area. So if you have some area and if there are some forces acting on it, so how much force acts per unit area? So this stress is nothing but the force intensity. It's called as a force intensity. And that stress will be defined as force by area. The symbol for that is sigma. So keep this in mind. So sigma is the symbol of stress. It's force by area, and that's why the unit will be Newton per meter square, or you can also use Pascal. So both are okay. So that is stress. Remember that stress is force per unit area. Oh yes, Ranjit, it can come, the dimensions and all that. Definitely it can come. Next, quantity is strain. These quantities sound similar, but don't get confused, you will get used to it. Strain has the symbol epsilon. Stress had the symbol sigma. So strain is how much does a body's dimension change as compared to the original length. So if this was an object, this was its original shape and size. When you deform it, that blue part is that extra part. So then I can say if this is the change, and if I say this is the original dimension, so strain is nothing but how much is the change in dimensions upon the original dimension. That's what it is, and the unit is not there because it's dimensionless. Remember that. So it's a dimensionless quantity. All these are scalars, by the way, or they do not have direction as such. Okay, so change in dimension upon original dimension is called as strain. That's your next quantity, guys. Suyash, I'll be working very hard for you. I want the same commitment from you guys also, because that is what is needed, guys. You need such dedicated teachers and you need dedicated students to crack the JEE examination. Without that, it is not possible. Just having students, but teacher is not into, no use. Teacher is into, students are not into, no use. You need that perfect harmony. Rightly you said. Hello Bhanu Prakash, welcome. Hello Ruby. All right, so let's get going to the next thing. Now the next thing that I want to talk about is something called as Hooke's law. Very important law. It says that when you deform a body, there is some stress that you apply on it, because of which there is some strain. Now please understand who comes first. Does strain come first or stress come first? stress causes strain. Strain does not cause stress. Understand that. Okay, so when you apply a stress, understand strain is produced. And Hooke found out that for small deformations, this stress and strain are proportional to each other, only for a small region. But if you stretch it too much, if you deform it too much, then stress is no longer proportional to strain. So that is what Hooke's law is. So when you stretch a body, you are applying some forces to stretch it, and he found out that if you plot stress versus strain graph for a small deformation, keep that in mind, it is going to be, alright, it is going to be a straight line. I hope you can see this dot going up and down. Why is it going up and down? When you load it, when you extend it, the stress increases, the strain increases. When you unload it, that is you relieve it of all the forces, it will come back. The stress goes back, the strain goes back. Do you see it is exhibiting an elastic behavior? Because if it is coming back to its original point, that means when I relieve it of its stress, then the strain also comes back. If it showed plastic behavior, then when I relieve the stress, it will not come back to the same point, it will go somewhere else. Because there will be some amount of deformation left over in spite of the stress being completely zero. So since it is coming back to the same point, that is why I'm saying it's elastic behavior. Now you might be wondering, sir, what happens after this point? We'll be coming to it shortly. Don't worry about it. So according to Hooke's law, alright, so according to Hooke's law, the stress is proportional to strain, but this is only for small deformations. Very important, it's not for all the deformations. And that ratio of stress by strain is called as the modulus of elasticity. This is called as the modulus of elasticity. Very, very important. Now you will be like, sir, what is the symbol of modulus of elasticity? Don't worry, I'm going to get there. But for now, this modulus of elasticity has an unit similar to the unit of stress, because strain is dimensionless, so the unit will be just newtons per meter square. Okay, so it is newtons per meter square. And if you plot a graph of stress versus strain, then understand the slope of that graph. Alright, so the slope, so this will be, let's say, delta y, or rather I should put delta sigma by delta e. That slope which is there, delta sigma by delta e, is going to give me the modulus of elasticity. So it will be modulus of elasticity. So it's the slope. Understand that. I hope you have noted down all these pointers. Alright, yes. So we are going to see how much deformation it can undergo. Yes, there is a special point for that. In stress strain curve, I'll be mentioning till what point is stress proportional to strain. After that point, what happens? We are going to discuss that in detail. Okay, so very, very important pointers. These are quick revision things, guys, for all the 11th, 12th and the dropper students. All 11th, 12th dropper students, this is all for you, so that you can understand every topic in detail, and we are also going to solve some problems now. Now, there are 3 different kinds of deformation that we have in JEE, guys. Very important. 3 different kinds, and these are the only types we have. Alright, so this is what we need to study. Now, one is when you stretch a body or compress a body, that is called longitudinal deformation. The second one, yes, Prajwal, will be going live at 4 p.m. today. Okay, and concentrate on the session, Prajwal. Now, another one is shear deformation, when the forces try to shear a body. I'll explain what shear is in a bit. And the third one is not for solids, it's for fluids, or basically liquids or gases. That is called as volumetric deformation. So 3 kinds of deformation that we are going to study. The first 2 is generally for solids. So for solids we have changes in length or the changes in the shape, that is longitudinal and shear. And the third type is only for fluids, which is called as volumetric or bulk deformation. So let's see each one of them in detail. Okay, now you might be like, sir, what kind of deformation is this? Well, now, is this longitudinal, is this shear, or is this volumetric? Now let me tell you guys what happens in reality. In reality, what engineers do is they make a model of this object. Okay, they make a model of this object and they divide any object like this. Okay, they divide any object like this into small cubes. Okay, small dx types. They make it into small cubes, and for any one cube they see how does this cube deform, how does the length change, or does the shape change like this, what happens to each cube, and then accumulating all the effects. Acha, this cube deformed this much, acha, this cube deformed this much, acha, this cube elongated this much. So combining, accumulating all the effects, you get the total new shape or the deformation of the body. So you'll be like, sir, isn't this a time consuming process? Don't you think so many cubes will be there? Because you're dividing it into small parts for modeling purpose. Yes, it will be there. And because of which, you know, it is being actually done using computer simulation. So computer simulations are basically huge. Computers are needed for calculating each of these deformations to analyze how these objects deform. So all the bending, or twisting or elongations or deformations in your aeroplanes, vehicles, structures, buildings, bridges, etc. they are first modeled on a computer simulation, and then they are verified whether it can actually withstand all these forces, all these random behaviors, and then it is actually constructed, because you won't approve the design unless it can actually withstand it in that computer simulation. So that's what happens. So presumably we will notify if something has changed, then don't worry, we will notify it. Okay, so don't worry about it. All right, so now having said that, let's talk about the first deformation. What is it called? Like I said, it is called longitudinal deformation. So longitudinal deformation means when you pull or push a body perpendicular to a face. Look at that. How is the force applied? Perpendicular to the surface. Then the length of it will change. That is called as the longitudinal deformation. L0 was the original length. You can see delta L is nothing but its new length. Okay. So that is called as longitudinal deformation. Very, very important, guys. So let's write about it now. So let's write about longitudinal deformation. So first of all, let me write down what will be the longitudinal stress. This force is acting on this area. All right, this force is acting on this area, stretching it. So the longitudinal stress will be the force upon area. Now, what if this force is actually not, perpendicular to the area? What if this force was at an angle? Then choose only the perpendicular component, because only that component perpendicular to the area is responsible for the change in length. So this F is only F perpendicular by area. Understand that it's not the total force. I know you are thinking, sir, what about the parallel force then? Don't worry, we'll come to it in a bit. So perpendicular force by area. Then strain, which is again longitudinal strain, is given by how much does my length change, delta L upon original length. So again, it's a ratio. Sometimes strains are also expressed in percentages. So say for example, understand, if the strain is mentioned to be 1%, that means if the original length was 1 meter, then the change in the length is 1% of 1 meter, which is nothing but 1 centimeter. So strains can be expressed in percentages or fractions. It's up to you. Okay. So now, if you have understood this, remember just some time back I had told you modulus of elasticity, which was nothing but stress divided by strain. It was just stress divided by strain. So just imagine if I divide stress and strain, guys, I will get modulus of elasticity. But when the deformation is longitudinal in nature, then that modulus is called as Young's modulus. So what is it called? It is called as Young's modulus. Very, very important for all of you to know that. Therefore, I can say that Y, which is Young's modulus, will be F perpendicular divided by area, the whole thing divided by change in length upon original length. So that's what it's going to be. Alright, I hope this is clear. So this is change in length upon original length. Okay, so remember this, guys, this is nothing but Young's modulus. Jagdish, I do not know whether NEET date is postponed. And Daniel, am I taking lessons according to NCERT to increase more content? So Daniel, I am taking sessions based on whatever I feel will be apt for your understanding in a particular order. It might not be exactly the same order in which chapters are there in NCERT, but these are based on my past experiences, that if students are taught in this particular manner, then they will grasp the highest content. Okay. So yes, Ranjit, the same Young of YDSC. Yes. Yes, Jagdish, even niche students can attend. No problem. As long as you are focused and you have the intention with the true heart to study, you are utmost welcome. Doesn't matter, you could be even a BTech student or even a 9th standard student. You are almost at most welcome. Okay. So that is the first thing that you have to study over here, longitudinal deformation. Now, in this situation, do you see the forces are outwards? And in this situation, the forces are inwards. What do you think is the difference, guys? Let me know in the chat box. Iron can have all kinds of deformation. Saurav, it's not expansion. Iron can expand, it can even contract, by the way. So what do you think is the difference between the two? Think about it. I feel that there is a small difference between the two. Come on, can you let me know in the chat box? Yes, the first one is expansion, the second one is contraction. Will this formula work only for extension? No, it will work both ways. Understand, for both the situations this formula will work, either for extension or for compression. So you don't have to worry about it. Okay. Second thing, can strain be ever negative? Can the value of the strain be negative? Come on, think about it. Can strain be negative, guys? Come on, let me know. What do you think? Can strain be negative? Come on, let me know. Come on, guys. Keep answering in the chat box. Let me know. What do you think? No? Saurav says no. Uncharted Jumna, Jagdish says no. Guys, strain can be negative. Yes. If you have been told that strain is not negative, that is wrong. Strain can be negative. How? If it expands, strain is positive. If it compresses, the change in the length will be negative. So strain will also be negative. So keep this in mind. If strain is positive, it is increasing its length or increasing its dimension. If strain is negative, then the dimensions are decreasing. So keep that in mind, because delta L can be positive or negative. Okay, I hope this is clear. Stress is not negative. Now, do you see this word called modulus? What is the meaning of the word modulus? Modulus means it should be always positive. Now you will be wondering, sir, the numerator is always positive. This you are saying is a modulus, matlab that is also always positive. Then you are saying strain can be positive or negative. How is that possible? So that's why in the actual definition what happens is, okay, so in the actual definition what happens is we put a modulus over here, because this can be positive, negative, both. But usually we write strain when substituting in the formula as a positive number. After putting modulus, we always put the mod value of the strain. So that's why you are always going to get a positive value. Remember that. No problem, Sneha, join in, it's okay. Stress is not negative. Stress is always a positive number. So usually my sessions are at 7 o'clock, guys, but today I have conducted the lecture at 2 o'clock because I'm going to be out of station starting today evening. So that's the reason why I have shifted the class to 2 o'clock. No problem. Okay, usually my timings are at 7 o'clock in the evening. I hope this is clear, guys. You understood the true meaning of modulus now, I hope. Okay, very, very important. Let's go ahead. Now look at this. If you apply a force like this to a object, the length changes, correct? The length changes. But if you apply a force like this, the angle changes, the shape changes. This is longitudinal behavior. This is longitudinal behavior. This behavior is called as shear deformation. So shear is when you slide two things like this. That is called as shear. Very important. Now things would be probably very clear in your mind. That imagine if there is an object on which the force is at an angle. If the force is at an angle, then don't you see that force will always have two components, one this way and one this way. This will be the perpendicular component, this will be the parallel to the surface component. What will be the perpendicular component responsible for? It will be responsible for the longitudinal deformation, the lengthwise deformation. What will be the parallel force be responsible for? It will be responsible for the shear deformation. Correct. Hello Ali, I'm very good. Nice to see you back again. So this is something that should be there in your mind, and you should know what's the difference between normal or longitudinal deformation and shear deformation. Very good simulation for making you help visualize these things. Not many students actually are taught this way and they never visualize this. That's quite a pity actually. More examples. Look at this. Look at this. Even this is an example, but I'll come to that. Taking a book and pushing it like that. Pushing it like that. So when you push the top surface of a book like this, each page is sliding over each other. That's a shear deformation. You'll be like, sir, I'm applying a force like this. Who is applying the force this way? Guys, that's friction between the book and the table. So there is a couple like force which is, making sure that the bottom point remains as it is, the top point moves like that. So that's the shear force which is pressurizing that book to slide, the book pages to slide over each other. The same thing is also happening here. I don't know whether you can visualize it. There is a nut between those two plates, and because you are pulling this plate down, you are pulling this left side plate down, there is a shear force acting on the bolt, or that that nail which is there inside, because of which that nail breaks. I hope this is clear. I'm very good, Ali. Welcome. Yes, angle will shear or motion thing. I didn't understand your question, Saurav. But basically shear force causes change in the shape and the angle will change. That's what will happen. Okay, if that's what you meant. So now let's talk all about shear modulus and shear stress and shear strain now. So how is shear stress defined? The way shear stress has been defined is the force which is parallel to the surface upon the area on which it acts. Look at that yellow color shaded area. So force upon this area, not any other area, is called as shear stress. Then shear strain is nothing but how much does that face shift, that is delta x, upon how much is the separation between those two faces which are sliding. This is one face, this is other face. The upper face has slided by delta x and their separation was, let's say, L. So that shear strain is delta x by L, and if the angle between them is theta, then delta x by L will be also nothing but tan theta. And if theta is very small, you can approximately say that it is theta only. If theta is small, this is nothing but small angle approximation, guys. This is very important. When theta is small, tan theta and sine theta both are equal to each other. That's a very important mathematical approximation. You should know this. Now, when you divide both of them, stress and strain, what do you get? Modulus. But in this case, you are going to get shear modulus. Shear modulus is going to be shear stress. Okay, shear stress by shear strain. And the symbol for shear modulus is G. Understand that. Sometimes it is also called as rigidity modulus. Rigidity modulus. One and the same thing. So G will be shear stress is parallel force by area, and shear strain is nothing but tan theta. So I can just put tan theta over here. So this is another formula which you should keep in mind. Very, very important. You should know all these individual definitions as well. Okay, very good. Yo, understood everyone? Shall we go ahead? Shall we go ahead? Come on, let me know guys if you guys have understood all these pointers. So many things should have been cleared by now. Okay, yo, very good. Last deformation, bulk deformation. Like I said, it is generally used for liquids or gases. So when you pressurize something, what happens is that the volume changes. And if you relieve that pressure, the volume increases. So that is nothing but a bulk or a collective property. Bulk means collective, as a whole. Alright, so as a whole, the volume changes because of the pressure changes. So that is what bulk is. So there is a small catch which many people do not know over here. I will tell you. Many people do not know this. Now listen to me. Now the bulk stress, alright, the bulk stress, you might be thinking it is pressure. You know? That is not true. Bulk stress is not pressure, guys. It is in fact change in the pressure. You will be like, what? I'll give you an example. Imagine if you have a balloon, okay, it won't change its shape unless the pressure from the outside changes. So let's say from outside the pressure changes, that's why the balloon changes its volume. So who is responsible for the change in the volume of the balloon? The original pressure or the change in pressure? Now that should answer why the stress for bulk should be delta P and not the original pressure. I hope this is clear. Yes, Jagdish, we are doing it for 11th as well as 12th, both. And there is a big playlist, you can check it out on our channel. All the videos are beautifully arranged chapter wise. Okay, next thing. So that's why it's very important, guys, you attend all these lectures, because all these minute details, right, if I do a one shot, will be skipped. Understand that. Only when you take individual classes, I have seen people doing one shot for entire mechanical properties in 1 hour. Guys, you only tell me how is it possible, you tell me if it is possible to complete entire mechanical properties, what I did in 4 lectures in 1 hour or 1.5 hours. It's impossible. And if you think it is possible, let me know. Okay, so this is nothing but again bulk strain, and bulk strain is change in volume upon original volume. Obviously the volume changed, so change in volume upon original volume. So the next thing will be bulk modulus. So next thing is bulk modulus, and bulk modulus, guys, will be change in pressure upon delta V by V. So it will be, basically think of it this way, guys, it should be bulk stress again divided by bulk strain or volumetric strain. Now the symbol for bulk modulus is B, so it will become delta P divided by delta V upon V. Now there is again another catch over here. My God, good, thank God we are here, or else so many marks would have been lost. Now I'll tell you what is the catch over here. The catch over here is, just think about it. Imagine you had a body and you pressurize it from everywhere, so the volume decreases. So will delta P, change in the pressure, be positive or negative? Think about it. Will delta P be positive or negative when you decrease the volume of some body? Think about it, guys. Think about it. Will pressure change be positive or negative? Pressure change. Jumna says positive, Saurav says negative, Fida says negative, Sneha says negative, Uncharted says positive, Ranjit says positive. So guys, the answer is it will be positive. Think about it, because my pressure increased, that's why the volume decreased. So pressure has increased, so delta P is positive, numerator is positive. Okay. Now what about the new denominator? Will volume change be positive or negative? Will volume change be positive or negative? Think about it. Volume change will be negative, correct. Bilkul. Very good. Now let's say I do the exact reverse. Let's say I relieve some pressure because of which the object expands. The object expands because I've relieved some pressure. So in that case, because I've decreased the pressure, numerator will be negative, denominator will be positive. Do you see that? Because volume will increase, pressure will decrease. In either case, what do you see? Both the numerator and denominator always have opposite signs. Now, what should the value of bulk modulus be? It should always be positive. That means if I know for sure that one of them is going to be always negative, doesn't matter who, but one of them is always going to be negative, why not put a minus sign here? That minus sign will take care that whosoever is negative, it will automatically multiply by -1 and make it positive. So that is why there is a minus sign, and if you did not realize it back then when you studied wherever, now I hope you have understood this. Very good guys, amazing. See guys, you are learning so much today. You thought that this chapter was a cakewalk. Arey kya seekhne milega? What will you learn about bulk modulus? But don't worry guys, you are attending Shreyas Sir's class. And you guys are minions. The faithful minions. Very good. The enthusiastic minions. Very good. So let's start solving problems. But before that, clear-cut distinction between all of them. Very, very important. So this distinction between all three of them, where I'll be giving some pointers. Okay, I'll be giving some pointers that will be coming up in something called as extracts. Remember, extracts are nothing but, the summary of every chapter. Yes, they are nothing but the summary of every chapter, and it is always there in either the Telegram group or in the description box below. And let me tell you where to find it. Now we are going to solve some problems. Hold on. We're going to solve some problems. But before we solve some problems, just 1 second. Let me tell you all about. 1 second. So where to actually find it? See, when you go to our home page, right? In any playlist, let's say, so you have a playlist like this. All right. So maths playlist is there, physics playlist is there. So each playlist is basically chapter wise, like you can see. So there is 1D kinematics playlist, there is 2D kinematics playlist, circular motion, momentum, fluid mechanics, electrostatics. So let's say you go to electrostatics and gravity, example. All right. So you will see all the lectures arranged over here. You can see that they are all beautifully arranged over here. Okay, one by one for your benefit. And if you check out the last lecture, always the last lecture, lecture 6 in this case, sometimes it could be lecture 3, sometimes it could be lecture 4. If you go in the description box, you will see the extract link, PDF link will be here. The session link is also there. So the session link is basically the workbook. So you can make notes from this workbook while attending this lecture. The extract link will contain basically all the important pointers, all the important formulas, all the important properties, methods, do's, don't do's, etc. Everything will be there in these extracts, guys. All the formulas, theory wise, is beautifully arranged in these extracts. So that is what you need to do. Okay, so do that, guys. and everything is beautifully arranged in the form of playlist. In fact, even when you visit the home page, right? When you visit the home page, if you just scroll down, you will see maths playlist, physics playlist, chemistry playlist, and all the important playlists for preparation for 2021, previous years, mega sprint, all these things are mentioned over here. Okay, so this is very, very important for you guys. So I thought it's beneficial for me to tell it to you right away. Okay, I hope this is clear, guys. Everyone clear about it? Thank you, Ranjite. Thank you, Vida. Apart from extracts, Ranjit, you also need my lectures, and you need a lot of problem solving and the books that I have recommended. All right. So before we go ahead, let me tell you, for all the 12th and the dropper students, there is a crash course which is starting every Monday. So you can check out all the details again in the description box below, where you will be having 10 full and 10 part syllabus test series, and all the syllabus will be completed in 120 live sessions, which are two-way interactive, and also there is a class teacher inside the class to solve all your doubts, and outside the class you also have the doubt app to solve all the queries that might arise. So go check it out, because it's going to be very crucial for clearing your JEE mains examination, which is going to be conducted 4 times, and the price for this crash course is 10,000, but you get 20% off after you use the coupon code SHCC. So use the coupon code SHCC, guys, and you'll be getting flat 20% off. That is the highest discount you ever get on Vedantu platform. Understand? So nowhere else you can get this high percentage discount. So you can also recommend this to any of your friends or relatives in case they are interested. All right. Sure, Jagdish, I will definitely reply. Just give me some time. All right. Generally, I take 1 to 2 days time to respond to all the comments. So let's begin with some questions. Get ready, minions. Get ready, minions. So if the stress is numerically equal to twice of Young's modulus, then how much will be the elongation? Come on. Let me know the answers in the chat box quickly. Waiting for you guys. Quickly. What do you think the stress will be proportional to? Come on, guys. Think carefully. Saurav says A, Jagdish says 4, Uncharted says D. Come on, everyone. Come on. All right. Most of you, I think, are saying it correctly. Saurav, I don't think it is 1/4, most likely. I'm not sure. But yeah, it's D. Now, why is it twice? See, guys, the logic behind this is, if stress is given to be twice Young's modulus, but we already know the formula for Young's modulus is stress by strain. Sigma cancels, so epsilon is 2. But what was strain? Change in length upon original length. So what will you get? Delta L is 2 times of original length, hence twice the original length. That's how simple it is. So this was a warm-up question. Don't worry, there are many more questions coming up like this. Next question. 2 parallel and opposite forces, each of 5,000 Newton, are applied tangentially to the upper and the lower faces of a cubical block of side 25 centimeter. What will be the angle of shear? The shear modulus is 80 gigapascal. 80 gigapascal. Let's see what do you guys think about this. How to do this problem? Let's see how to do this question, guys. Come on, any guesses? I'll just give you some time to solve. Option C, 100%. Come on, think. Okay, guys, I just got the notification saying that the live session with all the teachers, which was supposed to happen on 17th of December, has been shifted to 22nd of December. So guys, I think the 4 o'clock session will be shifted to 22nd December, not today. So guys, we'll be shifting that session. Okay, so please keep that in mind. So all the board announcements that were supposed to happen today will happen on 22nd December, not today. All right, so many of you have said D, some of you said C also and B also. There is no option which is left now. Okay, so the correct answer is option C. Now let us see why it is C. Okay, so the logic is, you have this block like this, okay, and the forces were like that. This was F, but the area that you should consider should be this area, and any one force. Please don't consider both the forces, guys. That will be stupidity. Okay, one force is a supporting force. It makes sure that the base stays there. The other force makes sure that the angle changes when the cube slides. So think about it. The question was the angle of the shear. So rigidity modulus G is stress by strain. And what is that stress? Well, that stress is force which is parallel divided by area divided by tan theta. But when angles are small, tan theta is almost theta. So theta is almost F parallel by A, and that G comes downstairs. Now just substitute everything, guys. The parallel force is 5000 Newton divided by area. Now side is 25, so 25 square, all right, but it's centimeter square, so convert it into meter square. And lastly, do not forget the value of G. G is 80 gigapascal. Now giga is 10 to the power 9. So kilo is 10 to the power 3, mega is 10 to the power 6, giga is 10 to the power 9. Okay, so that is something you should know, kilo, mega, giga. So solve this and you should get this as 10 to the power minus 6, but the answer will always be in radian. Okay, no idea, Jagdish, about that. No problem. I hope this is clear. Let's get going with the next question coming up on your screen. If a rubber ball is taken down to a depth of 200 meters inside a lake, the volume decreases by 0.3%. G is 10. Then the bulk modulus of elasticity is how much? Come on, let's see how many of you get this now. Giving you some time. Think about it. What will be the bulk modulus? Think about it. Think about it. Come on, guys. What would be the bulk modulus? Okay, looks like people are finding this problem difficult. So let me tell you guys, it's not that difficult. All you need to do is just think, when that ball was actually on the top, it had some volume, but when it went below, by how much depth? It went below by a depth of 200 meters. This depth is going to definitely cause some pressure change, and that's why you're going to see that the volume decreases. So what you need to do is use bulk modulus formula. Bulk modulus is delta P upon the change in the volume's strain. So it is 0.3%. Now 0.3% is nothing but 0.3 into 10 to the power minus 2 in magnitude. It's percentage, right? So divided by 100. So that is how you will get it. So remember that here you should put the value of strain. So delta P is going to be rho GH, and this will be epsilon. Why is it not P naught plus rho GH? The reason why P naught is not there, because remember, this is change in the pressure. When it was on the top, the pressure was already P naught. When it is at the bottom, it is P naught plus rho GH. So who is responsible for the change? This term. So this is responsible for the change, guys. Now just substitute everything. Rho is 1000 or 10 to the power 3, G is 10, height is 200 meters divided by the strain. Where is the strain? Strain is 3 into 10 to the power minus 3. Alright, I can write 0.3 as 3 into 10 to the power minus 3. So you can see that this is going to become 2 by 3. And if you count the zeros, 10 to the power 6, 7 and 9. So this will become into 10 to the power 9. So this is nothing but 0.67 into 10 to the power 9. I hope this is clear and understood. Very, very important. Alright. So let's get going to the next question, guys. Get ready for the next question coming up on your screens. Now, this is a very good question. Alright, this is a very, very good question. The question says, if there is a rod which expands because of its own weight, then find the elongation. Okay, if a rod expands because of its own weight, then find the elongation. So let's try and do this problem. Now, the red one is the original length, the blue one is the extended length. Don't worry about options. This is like an integer type. Think of it like a subjective type. So, how to calculate this? Understand, in this problem, when the rod is expanding because of its own weight, the stress is different at different locations. No, the force is not mg. That's the common mistake. That's where people go wrong. The stress is not same. Why is it not same? Because at every point the force is different, guys. Understand that. In fact, if I had to show you, understand this. If this was our, or rather, one second. Draw it here. If this is our rod, guys, okay, if this is our rod which is supported at the top, please understand the tension everywhere won't be same. Now, why won't it be same? Let me tell you. Just imagine if I consider a section of that rod till only this much. Let's say I consider only this much part of the rod. Only this much part of the rod. At this point, think about what the tension must be. At this point, the tension must be how much ever weight is there below it. If I go above, that tension will be the weight below it. As I go more and more up, you will see guys, the tension keeps increasing. Reason? Because more and more weight is there below. So understand, this is a proper advanced type of question where the tension keeps varying. Over here the tension must be zero because there is nothing below it. Imagine you are holding somebody's leg, that person is holding somebody else's leg, that person is holding somebody else's leg. What do you think will happen? Who will have the highest tension? You or the person on the top? Obviously the person on the top, because he has to support the entire weight. The person at the bottommost point will not have any tension. So the tension keeps increasing in this problem. That is the question. Correct. So let's assume, guys, this much distance is x. This much distance is x. First you need to figure out how much is the tension. Now for that, what I will do, let's think how much mass will be present over here, because I will need that. Understand, for a length of L, that mass was capital M. Total mass of the rope or the rod was capital M for the total length L. So for a length of x, how much is the mass? The mass is M. How much will it be? Isn't it unitary method? So think about it now. What will be the value of m? It will be m by L into x. This is unitary method, mass per unit length into x. We have been doing this many times. M by L, total mass upon total length, is going to give me mass per unit length into x meters, will give me the mass of that many meters out there. Correct. Now the tension at that point T will be small m into g. So therefore it will be capital M G x by L. So that is how tension changes with x. That's how tension changes with x. Very, very interesting result that we got. Now that we have got this result, the problem is not yet over. The stress will be tension by area. So A is that area of cross section out here, this area. So this is this area. Remember that length L that I was talking about was this. Maybe I can use capital L symbol. Okay, so this was that total length. Okay, so now what to do? Just substitute the value of everything. So it will become m g x by L A. Interesting. Now that I have found out stress, now observe what and all things happen. Let me write it over here only. Mass is density into volume. Do not forget that. So let's use that. So sigma will be equal to rho, which is the density, into volume. What is the volume of that rod? It will be the length into the area. So it will be rho L A into Gx divided by, again that LA is there below. So LA cancels and you will get it as rho Gx is nothing but sigma. So I have found how stress changes in the given terms. Density, G and X, everything are there. What a beautiful question till now. So this is how advanced questions are. And sometimes this can also come in the integer type or numerical type of questions in JEE Mains. Remember, even this year there are going to be 10 questions in JEE Mains which are going to be of numerical type. That's what they have announced. Do not forget it. Okay. Now that we have figured it out till here, let me just get rid of this. It's no longer needed. Now comes the next part. You'll be like, sir, what is next? Guys, I need to think about a section. Okay, so let's think about a section of that string or that rod, and each section will have different elongations because each section has different stress. So I need to add all those elongations to get the total elongation. That's the problem. Each section has different elongation. So I've just shown one section here. Just imagine that particular section, all right, elongates by so much. Just 1 second. Yeah. All right. Crazy to draw. Okay, all right, so now I think it makes sense. All right, so what is happening, guys, is this much is the elongation and this much is nothing but the original length. So each section of that rod elongated by so much, and I have to add all those elongations. So let's assume those variables. At a distance x, let's assume the thickness of that section to be dx. So this is a section of the rod, but this is original section. This change in the length, this is nothing but the change in that length, and that one I'm going to assume it as d small l. Don't assume it as dx because dx has been already assumed. Yes. So this is dx. Why dx? Because dx will give you the total length. dl will give you the change in length. They are two different variables representing two different quantities. Addition of x's, total x will give you total length. Addition of dl's will give you nothing but, the total change in length. I hope this is clear. Now, think about it. If I ask you, what is the value of strain produced in this part? What will your answer be? What is the strain produced in this part? The small section which has elongated by dl. Guys, be careful. This is the change in length. So this will be dl divided by original length, which is dx. Very interesting. Change in length upon original length was dx, that has expanded by dl. So that is the strain produced over there. Now the problem gets simplified, guys. There is nothing more left to it. It's simple. I'll tell you why. Because Young's modulus, remember, was stress by strain. So it will be rho gx divided by dl by dx. Now just rearrange these terms. Okay. So dx will go on the top, dl will go here. So it will become dl is equal to y has to be taken down here. So rho g by y, dx goes with x, multiplies like this. Now this is in a beautiful form which can be integrated. And now I'll put the integral symbol over here, and I will now think about the limits of integration. If I start with the first section here, I start with the first section, how much it elongated. Next section, how much it elongated. Next section, how much it elongated. I have to add all the elongations. So I'm going to start when x is 0, the elongation will be 0. Because there is no tension over there, there is no elongation. But when I go to the final section, which is at a distance of capital L, the final elongation will be small l. This is small l represents the final elongation. So integration of dl is just l. So it will become l minus 0. When you substitute the limits, you should know definite integration for solving this is equal to rho g y by y, and x dx integration is x square by 2. So it will become l square by 2 minus 0 square by 2. That's how you do definite integration, right? X raised to 1, integration is x raised to 1 plus 1, which is x square by 2. So x square by 2, but you have to put L first and then 0 next and subtract them. That's how you do integration with limits. So L will come out to be rho g L square by that 2 and y. And that, my dear friends, is the final answer. So what a problem. What a question this was. I hope you guys understood this. Is it clear, everyone? It's up to you, Nifa. I will be doing JEE Advanced problems as well and JEE Mains question as well. So JEE Mains is similar to NEET, but these kind of questions are purely the good questions of JEE Mains or questions of JEE Advanced. So as long as you have the intention to learn, you are definitely welcome. Okay, excellent, guys. So let's go it going. Clearo? Very good. So that was the answer for this question. Now let's talk about the last two things in this chapter. The last two things in that, the first is elastic potential energy. So we know that whenever you stretch something, there is energy stored in it. That is called as elastic potential energy. So just like you take a spring, you deform it, there is energy stored in it, because when you leave it, you know it's going to perform some work. So the energy stored in any elastic body is called as elastic potential energy. Now, if you take any body and you elongate it, say for example, it had some length L and you change the length by X. Okay, so this was the original length, and you have applied some force. This was some area. It had some Young's modulus. So we know that y is equal to force by area upon change in length upon original length, correct? Now you rearrange this, you will get F is equal to y, area comes on the top and L goes on the top and again comes below, and X again goes here. So F is YA by L into X. Now this looks very similar to F is equal to Kx. When do you use F is equal to Kx? Guys, for spring. You have a spring, the spring elongates by X, that force which you apply is given by F is equal to Kx. So very important to remember now, this quantity over here, okay, this quantity over here is called as the equivalent spring constant. This can be very useful for solving problems, correct? So I hope you remember the energy stored inside a spring. It was half kx square. So instead of k, just put this. So it will be YA by L, that will be k, into x square. That is the elastic energy stored in a deformed body. As simple as that. Okay, very simple way to remember it. Half kx square. That's one thing. Now there is also a second way. No, it will not be negative, it will be positive. Energy stored will be positive, it will always store some energy. Now there is another way of writing it. If you divide this elastic potential energy with the volume, it is called as energy density. It is called as energy density because the unit will be joules per meter cube. Joules per meter cube. You can give it the symbol rho but U. So density but energy wise. So that's why the symbol rho U. So elastic energy density, when you solve it, alright, you can solve it, it's not a big deal, comes out to be half stress into strain. So this is another way also of writing it. So energy per unit volume is half stress into strain, or you can also think energy is half stress into strain into volume, one and the same thing. It's up to you how you want to write it down. So both are very, very important forms. Both are very, very important forms. Equivalent spring constant and energy density. I hope you are writing all these things down. Now let's solve some problems, but before that, the last concept, like I was telling you, let's come to that. Now you would have tried this, guys. Try to pull something, like take a rubber band if needed. Take a rubber band if it's lying around, and if there are girls out here, they can probably take it out from their hair if you are wearing one, alright, or pull it from your brother or sister if they have one, alright, and just stretch it. You will see when you stretch it, there is some stress you are creating and there is some strain. You pull it more stress, more strain. Leave it, no stress, no strain. Again pull it, stress, strain, both will be there. Leave it, no stress, no strain. Now pull it till a point, you leave it, you see that it does not come back to its original shape. Yes, it happens. You extend it so much that it does not come back to its original shape and size. That means you have crossed the Hooke's law limit. You have stretched it so much that you have deformed it completely. You have crossed the elastic limit of that material, and it comes back but to a different shape and size. You have crossed that elastic limit. You have entered a zone called as the plastic zone. You entered something called as a plastic zone. So in the plastic zone, when you apply so much of stress, you have deformed it so much that it comes to some new shape and size. Now you are more excited, so you pull it even more, you will see the spring or that rubber band will break. So you have crossed all limits, it has broken, so you have reached the maximum strength of that material. In that case, it would be rubber. So every material exhibits these kind of behaviors. So when you pull something, there is a lot of stress developed. The blue one says less stress, green says more stress, yellow means even more, red means even more stress. So when you pull something, the stress keeps increasing, the colors signify where the stress is more, and eventually what will happen, it will break, it will give up. It will break and it will give up. So when you pull something, eventually it breaks, but if you do not pull it too much and you leave it, it comes back, but sometimes it comes back to its original shape, sometimes it doesn't. So that is given by stress strain graph. So on the y-axis you have stress, on the x-axis you have strain. This is origin. From here to here, very important points I'm going to give you guys. Oh my god, Aarti just lost an hairband. So sorry Aarti, I didn't know. Okay, so I hope you get a new hairband. Alright, so Shiv Dhanush, kya baat hai Saurav. Okay, so first the stress goes up, strain also goes up. If you leave the stress, that's it, it also comes back over here. Now this only happens till a particular limit, guys. Now this limit, okay, be careful, what am I calling it? I am calling it proportional limit. I don't have space. This is called as proportional limit. After this limit, what happens, guys? Okay, it is no longer proportional, it behaves in very weird way. So till another point, that point is called as elastic limit. This is called as elastic limit. Understand, the graph is two-way in this region. That means if you relieve it, it will come back to the same point. Understand, it will come back to the same point. But if you go beyond this point, this is just one way. Like you have two-way roads, two-way traffic. This is just one-way traffic, only one way. You cannot come back, because if you try to come back, you will see that you will reach somewhere else. Now, what does this point tell you? This tells you that when there is no stress, still there is deformation. How? Because it was permanently deformed. So this is nothing but your permanently it has set itself, or it has permanently deformed itself. When there is no stress, there is still some strain. So if you go even further and leave it over here, then it might come to some new point. So this is called as the plastic zone. What is it called? It is called as the plastic zone because it behaves plastically. Yes. Now there is a limit to this also, and at this point the value of, or this point I will say, is the point where you have max strength of that material. Beyond this, anything what you try to do will just break, it will fracture. So it basically fractures at this point. Very, very important. This elastic limit also is called as yield stress. Y-I-E-L-D. Yield stress is elastic limit. Remember that. All these values, these graphs should be very, should be remembered. You should know what each point is. Now the last thing in this, by the way, I think I told you that the slope, alright, so slope in elastic limit, what does the slope in elastic limit give you? It gives you the Young's modulus. So the Young's modulus is the slope of this graph. I think I had told you this. It cannot cross the maximum height, Saurav. Basically, if you try it, it fractures, it breaks, the bonds are broken. You have crossed the limit. Now one last thing which nobody tells you guys. If you take the area, because these kind of questions have come in JEE Mains and JEE Advanced KVPY. If you take the area, now nobody knows what the area gives you. So this area gives you the energy density. Half stress into strain. You can see it very easily. If you take a triangle like thing, half base into height, half sigma and strain. What is it? Energy density. So that's the area. Very, very important. So the area under this graph gives you energy density. Okay, but it can only give it till this point, because understand, once it enters plastic zone, it is no longer elastic, so it cannot be called as elastic potential energy. There is nothing like plastic potential energy and all that. It's just not there. It does not store energy. So do not talk about these energies in this zone. Very important. No problem, Jumna. I hope you will be able to watch the replay, and you can also scroll back every time to watch what has happened. Okay, even during a live session. Okay, so this is very important. Let's start solving questions. So I just simulated the graph for all of you. So as the stress increases, as you pull it more, the strain also increases. But once the proportional limit is reached, the graph bends and it reaches elastic limit. Okay, it reaches elastic limit. That's what happens. So let's start solving some problems, guys. The stress strain of two materials are given, okay, and the graphs are drawn to scale. Which one do you think has more Young's modulus? Which one is more stronger? Okay, so to solve this problem, just think whichever has more slope. So if you look at graph A, I don't know whether you can see it from that side, but if you look at graph A and graph B, this angle is slightly less, this angle is actually more. So since this angle over here is more and this angle over here is less, you can measure that approximately. All right, so that's why which has more Young's modulus? That will be A, because more slope. Remember, modulus is decided by the slope. Which has more strength? For that you need to see the topmost point. The topmost point, this one or this one. Now I don't know if you can see this, but there is actually a very small difference, guys. This is slightly on the higher side. This is slightly on the higher side. All right, if you draw it, okay, so basically B will be the answer for that part. So you just need to check the highest point, that's all. Okay, so that's how it is. Okay, let's go to the next question. So 4 lines are given, load or force versus elongation is given. Force versus elongation. They are for different wires but same material, same original length but different cross sections. Which one do you think is the thickest wire? Which one do you think is the thickest wire? Come on, come on, come on, guys. Which one do you think is the thickest wire? Come on. A. All right, let's have a look whether it makes sense. Just some time back I told you force is of the form Kx, where K is nothing but Ya by L. So you can use this formula. Now you can see that in each graph the force is proportional to x. So this will then become your slope. So the graph which has the highest slope will obviously also have more area, because Young's modulus will be same. Why? Because same material and the lengths are also same. So Y and L are same. So wherever area is more, that's where slope will also be more. So that's it. OA will have the highest slope. So option A is correct. I hope this is clear. No, D is not the correct answer. Uncharted Sri Janvi. So be careful. Be careful. Okay. Chalo, let's get going to the next question. I hope you guys are understanding this. Coming up with the next question. The breaking force of a wire is F. When the thickness of the wire is halved, then the breaking force will be question mark. Come on. The breaking force of a wire is F. When the thickness of the wire is halved, the breaking force will be how much? Very good, very good. Come on, guys. B, D. Come on, be careful. All right, come on. The answer is, by the way, D, guys. Why is it D? See, the breaking force for a wire is F. Remember, in that graph which I had drawn, there was something like ultimate or final strength of that material. So for a given material, the value of sigma is basically fixed. You cannot change it. So for iron, there is a value of sigma. For aluminium, it's a different sigma. For plastic, it's different. So sigma is something which you cannot change for a material. Now what is sigma? Sigma is force by area. Stress is force by area. Now when you change the thickness, okay, now before that, how is area related to thickness? I think it is related to square of the thickness. Like say for example radius, pi r square is area. If you take square cross section, square of the side is the area. So it will be something k times of the thickness square. Now this gives me the answer. If thickness is made half, the square of it is made, think about it guys, think about it. The square thickness of the wire is half, then what will happen? Square of it will become 1/4 of it. Now if denominator becomes 1/4, what should happen to the numerator? It should also become 1/4 to keep the ratio preserved. In order to preserve the ratio, if denominator becomes 1/4, numerator should also become 1/4. Shalini, can you please ping me on Instagram? Really, I can help you. Okay, so if you are depressed, don't worry, we are all there for you. We will definitely help you out. Please ping me on Instagram. I will definitely be ready to counsel you, or you can also post it in the comments if needed. Okay, please do that. Okay, my Instagram handle is already mentioned in the description, but in case you do not know, it is Shreyas_Vedantu. Shreyas_Vedantu. That's my Instagram handle. Alrighty, let's go to one last question, guys. A metal rod of this Young's modulus undergoes this much strain. What is the energy per unit volume? What is the energy per unit volume? Come on guys, think about it. What do you think is the energy per unit volume stored in it? Young's modulus is given. Come on, think. Options are also there. C or something else. Come on guys, come on, think. Alright, so let me tell you, the correct answer is option A. Yes, very good Shreya, Uncharted, very good. So why is it A? I'll tell you. Energy per unit volume, if this is asked, that means rho u is asked, which is half stress into strain. Now remember, Young's modulus was stress by strain. So what will be stress? Young's modulus into strain. So substitute it over there. So half Young's modulus into strain, which will be half Young's modulus into strain square. Now I know everything guys. So rho u will be half Young's modulus is 2 into 10 to the power 10 into strain. Strain is 0.02%. So this is actually 0.02 by 100 guys. Be careful. Okay. So it will be 0.02 by 100 and the whole square. Now you can see what will happen. This will become 400 joules guys. Alright. So that is what you are going to get. That is what you are going to get. That's the answer. Just solve it. It's very simple. Everything is going to get cancelled. So many things are very easy to solve over there. All right. Now these are the stars of our previous session. Simran Mohapatra, Fida Nizar, Science Priya, just for the comment minions, and Saurav. And look at the interaction between you guys. I was just reading through all the comments and the interactions you guys had, debating and also asking how you did that, discussions happening. Very good. Keep it up guys. Congratulations. So all those students who are going to comment the answers of today's homework problem, I'll be posting their screenshots in the next session. So what is today's homework problem, guys? So today's homework problem is this. So post the answers in the post it in the comment section below after the session ends. All right, so post it. This is your homework problem. It will be also there in the session PDF, so go check it out. And I'll be posting the solutions of all the homework problems I had given to you in the Telegram group. The Telegram group's link is also mentioned below. Do not forget to join it. And I hope many of the 12th and the dropper students are going to be interested in the crash course. We'll check out the link, which is again there in the description box, and also get the benefit of 20% by using the coupon code SHCC. All right, so that's the coupon code you need to use. The batch starts every Monday, so you will not miss anything. So that's one promise we make. Okay, so that's it, guys, today. I hope you have enjoyed the class. We are done with mechanical properties. Next week, it's all about KVPY sessions, errors, measurement, KVPY for 12th, and there is going to be a special strategy session on Monday, because I'm going to be on leave, guys, Friday, Saturday, Sunday, but my lecture will be played tomorrow. It's a recorded one which will be played tomorrow at 7 o'clock. So do check it out. It will be on capacitors, but I will be otherwise seeing you live on Monday. And let's see if I can go live on Instagram too in these next 2-3 days when I'll be out for a vacation. But until then, bye-bye, take care, and I hope you have already smashed that like button out there. So bye-bye, guys. This was Shreyas here, your master teacher for physics.